Hello. Today we are going to discuss about the assignment number 7 of the dealing with materials data collection analysis and interpretation course. So, so we have so far discussed about discrete variables and discrete random variables and their associated mechanics, probability mass functions. And we have solved several problems in the previous live sessions. So some of the videos were a little delayed due to personal reasons, but from here onwards, from 7th to 12th, all the videos will be coming up on time. So I apologize for the wait to upload it. So yeah, before going into the problems, I just want to give a brief idea about the continuous random variable and their associated distribution. So okay, let's go into that. So what is continuous probability distribution? So continuous means like something we take it on a range rather than a individual values. For example, if you want to analyze the people who are using the phone, statistics based on the phone, which is like very common these days. So let's take that example. So if someone is using, so if most people have started using phone from the ages from 10 to 60, and we want to find what is the average hours, let's say like what is the probability that on an average a person uses the phone for 4 hours. So this is like very we are specifying a particular value here, like 4 hours. So this is like discrete value is very clear. But if what if we want to know like the people who use the phone on an average, so on an average from 3 to 5 hours like that. So that is like continuous distribution. So yeah, and also we specify a confidence interval like a 95% or 97% confident that people are using phone from 3 to 5 hours. So that additional data also being provided in the continuous probability distribution. So because like it has large number of data, we can provide more information in case of continuous probability distribution. And also we do a lot of stat hypothesis testing to arrive at the required conclusion in case of probability distribution. So okay, let's go into the types of probability distribution. So in continuous probability distribution, so it is further divided into like there are several distributions within that. Let's see one by one. So first question is the data is symmetric or asymmetric? So if the data which we have acquired, because we readily have the data with us, so the readily data available with us. So first we will see like how the data is based on the trivial problem. Like the data is symmetric, then uh, it can be like fall into the any one of these distributions. So further, if you want to see this, okay, let's say it is symmetric. Is the data is clustered around the central value? If the answer is no, then it is uniform distribution because it is not it is symmetric but not clustered around the center. Okay, if the data is clustered around the central value, yes, which means like it needs further information. How their outliers are. If the outlier doesn't have any outlier and the range or the outer values or the extremes are within the data points means it will follow a triangle distribution. So you can see, right? So if they have very low outliers, so very low outlier means they follow normal distribution. We can see this the extremities or the tail being very thin. So in this case, they follow the very for very low outliers, they follow the normal distribution. When the outliers are low, means not very low but low, then it follows Cauchy distribution. Cauchy distribution is similar to the normal distribution, but their peak is little sharp and their tail is little broad compared to the normal distribution. Okay. So this is what like when the symmetric data, when you have a symmetric data, your data might fall into any one of these distributions. So that is what I wanted to conclude here. And what if the data is asymmetric? So if it is asymmetric, then the next question, immediate question is like, where do the outliers lie? The extreme values, where do they lie? If they are like only on the positive side, like you can see here, right? The outliers are only on the positive side, negative side only, it doesn't have any outliers. Then they follow this exponential distribution. But when their outliers are mostly positive, then they follow this log normal, either they follow log normal distribution or gamma distribution or variable distribution. Even it can form the chi-square distribution. These are all like special kind of distributions which we will be discussing in the further course. So let's see another special distribution, which is T distribution. T distribution is a special case of a normal distribution when the sample sizes are smaller. Like this is also called as when the sample sizes of this normal distribution is smaller. That's why you can see here, right? They have given the line here, which means like the sample data whichever we are taking is smaller than the normal distribution. So in that case, we can it is better to go with T distribution because T distribution has additional parameters such as degree of freedom, so it can handle this condition better. So T distribution is a special case of normal distribution where the sample size is small, and this T distribution is also called as the student T distribution. This is mostly used for many hypothesis testing. We will discuss this further. Chi-square distribution also we will discuss it further in the upcoming questions. So let's go into the first question. Now we have an idea about the continuous probability distribution functions. So now we can answer this question better because here their question is the peak in an XRD profile is best represented by a combination of dash and dash distributions. So if you take an XRD peak, just a minute, let me take my time. To take an XRD peak, the peak is not like delta. Delta peak means you can see like it will be straight. So it will be like a straight line. They won't have any what is it? Any broadening. But in the case of but in the case of XRD, it is not a delta peak. Rather, they spread out at the bottom, but they are like sharp. They are like little sharp at the top. So we need a function which has to fit this. Means taller peaks or sharper peaks at the top and a broader peak at the bottom. So for this purpose, um, if we just use the on the right, you can see here now. If we just use the Gaussian distribution, the bottom part of this won't fit properly for the XRD curves. This is this is these functions are used in the Rietveld refinement of then phase distributions for an XRD. because first they fit the curve, bent curve for face identification test. They fit the curve and based on from the curve they do various analysis like how much fraction of the face present like that. But for retail refinement, we also generate the XRD profiles. Hence, in these two conditions, selecting the function is very important. Hence, we have to. It is better to use both the combination of this Gaussian or and Laurentian. Laurentian can also be called as the Cauchy function. So the correct answer for this is correct answer for this Gaussian and Cauchy. Let's see, like, why can't we use the other functions? Because like Gaussian is fine. Okay, if you're taking the first case, Gaussian is fine, but exponential is like just you have seen here. It doesn't even come close to the symmetric codes. So most of this scientifics are symmetric. So in that case, the fit won't be good if you are using the exponential function. So Gaussian is fine, but exponential is not what a proper function to use. Similarly, if you go for the third one, again exponential is coming. So whenever exponential or uniform, this is the worst case because at least in the previous cases, some part will be some regions will be fitted with the Cauchy function, but in the case of last one, can't we can't even fit the function using exponential and uniform because as you know, uniform will be like a straight line, and exponential will be coming like this. Hence, it is not advisable to use these functions. Yeah. So let's go to the second question. I think now it is very clear why we are using Gaussian and Cauchy function. Second question they are asking the probability that a classical, identical, and distinguishable particle in an average state V is given according to the Maxwell-Boltzmann distribution. Right. Okay. They are asking which equation which is well suited to represent the energy state in the state of a particle which is like identical and distinguishable particle, which is an identical and distinguishable particle. So, energy state or electronic configuration, all these things are described with the probability distribution function (PDF). So here also, like what are all the four, whatever they have given, are representing the probability density function. But which one is well suited for their above condition is depends on their Maxwell-Boltzmann distribution itself. Because Maxwell-Boltzmann distribution uh, is given by f of e equals to by exponential of minus e of e by is what widely we are seeing for the Maxwell-Boltzmann distribution. Here, Z is a normalizing parameter. Here, instead of in this question, instead of Z, they are using A. So, normalizing parameter here, factor of parameter, and what this exponential function tells us is, with increase in temperature, with increase in temperature, what will happen? This is exponential, not minus. It is at the top only it is minus. The bottom it is plus. With increase in temperature, the bottom value increases, denominator value increases, and total value decreases. So the probability of finding a particle when the temperature is high is very low because they will be moving in a random space. Hence, it is difficult to find their energy level or energy of the particle. Hence, at low temperature, they will be like moving towards the station, like particularly when they are coming close to the zero Kelvin, absolute zero. So that point, they will come to a stall, and it is easy to calculate their energy level. But in this case, when the temperature is increasing, the determining their energy levels is very difficult. Hence, the uh, probability of particle having that energy level will also be very. So here, the question which is like something very close to this is the first one. Second. Yes. So here, let's see what is E in the energy state. Like for example, if you are asking whether a particle is having two EV means two EV is the energy state or energy of the particular particle. Then K is the Stephen Boltzmann constant. Then T is the temperature in Kelvin here. A is the normalizing factor. What this A does is like the A helps to keep the normalize the value so that the value will lie between 0 and 1. So A does that part. And this is like one problem which we have taken from a book. System of particle is at temperature of 300 Kelvin. We want to find the probability of the particle being in the energy state of 2 electron volt. This is very easy because all the data is given. Just we have to take the Stephen Boltzmann constant from the reference and just have to plug in. So I will just leave that to this. Here I will just give the representativity how they will look like after substituting the values. The copy is given by uh, A the normalizing factor, the exponential of minus 2 divided by A in electron volt temperature in Kelvin. Once you substitute this, we will get the value. So that is the probability of a particle which you have randomly chosen, which will have 2 electron volt as the energy state or energy level. So let's move on to the third question. Before moving on to the third question, we want to know like we have discussed this before for this color play graph. Uh, let's quickly do a recap. So do you remember what is the meaning of schooners and what process? Anyone? Okay. So let me summarize that. Skewness is the measure of the asymmetry of a distribution. Like skewness is high. Distribution is like this distribution will be tending towards symmetric. For example, the positive value of skewness indicates the right skew distribution, where the tail is longer on the right side, and the negative skewness value denotes that the distribution is skewed towards left side, where the tail is longer on the left side. So typically, the skewness value can range from negative infinity to positive infinity. As I told, the value of that the value of the number tells that how much skewed they are. So, and zero indicates a perfectly symmetrical distribution. So, if in case we want to check whether your distribution falls exactly in the symmetric side or not, you can just calculate the skewness and see. If it is zero means it is perfectly symmetric. If it is close to zero means it is tending towards symmetry. Or else if it is if it is positive or negative means, for example, let me tell you. This is perfectly symmetric. I mean, in my way. Sorry for the delay. That's just against is equal to zero. Then for a positive skew, the tail will be on the right side. Skew, that's better and over. Then negatively skewed. Sorry, negatively skewed. The skewness value is less than zero. So based on this, we can come to skewness is good, very good in understanding few things because, like, let's say, like you have a population which is like perfectly symmetric normal distribution, and you are taking a sample out of it, and you are giving medicine. That everyone is taking that medicine, and you are after 2 days or few months, you are observing the okay. Let's say that sample whatever you have taken is having disease like a diabetic or something. So you have given the sample, you have given the medicine to them, and you are checking whether what is the diabetic level in a given interval, and you are plotting the results. Like if it is they are feeling better, the value will fall into this. Like if you take the exercise as betterness, the value will fall into the positive side. If they are like this, if they are not feeling better, the value will be falling. Like sorry. The value will be falling on this side. So positive skew means the result is negative, and the negative skew means in this case I'm telling the people who have tested with this medicines are having good results. So that is what the meaning is. And if it follows exactly like the normal symmetric distribution of the population, then it is very clear that there is no significant impact of the medicine on the health of this patients who have tried the diabetes. So, and Curtis, as I said before, they tells how their tails are like. It's like basically characterizing their tails. So tortoises can be uh, less than three, which means like they are negative, indicating the distribution with less extreme values or lighter tails than the normal distribution. Equal to three means the distribution has same tailness as the normal distribution, and greater than three means indicates a distribution with more extreme values and heavier tails than the normal distribution. So this is what the this can be used for in metallurgy. For example, in metallurgy we know the peak Brownian. So the exotic peak is so this let's say this is a peak. Um, It has kurtosis is equal to 3, which means like it follows a normal distribution. If it is like if it is a perfect crystal without any defects means they can look like this. They can look like this. K less than 3 for this. Because it doesn't have much extreme values. Here you can see these are the extreme values. This has only a lower extreme values. So it tells that the kurtosis value is less than 3. It's an indicator of that. And in other words, how we can say is if the peak broadening is more due to some metallurgical aspect or instrumental broadening, then we can see the peak being like this. This will have higher extreme values, indicating the kurtosis value is greater than 3. So in this way, we can remove the physical meaning in each application. Based on the application, the physical meaning will change. This similar can be applicable in a different way. Those kurtosis and spinors, we can use it in the different applications like civil engineering. But I'm not aware of their application. I'm just telling like just think about it and learn how you can use these things. Okay. So, for example, I can give one more example in case of meshes. In metallurgy, let's say if I'm adding a element to the aluminum, the name is the base metal, and if I'm adding what element like copper, and I'm seeing how the and before addition, I have taken the samples like say 1,000 samples, and I have taken the average value of their yield strength and yield strength values like this. And after copper addition, if I see the yield strength value tending towards this side means if the skewness is higher on, so if it is negatively skewed means then it is a good sign for me because the yield strength is on increasing trend. If the skewness is like on the negative side means if it is positively skewed means the extreme values are tending on the left side, like the intensity is more on the left side, indicating that there is a decrease in strength. If the skewness is zero means, then it clearly indicates that there is no significance in the addition of this copper to the. Similarly, I can, if I'm in a mechanical testing field, I can use this kurtosis to tell how my what is the reliability of my testing is. Let's say if I'm buying equipment, like if I'm planning to buy an equipment from two companies, let's say X and Y, and X company has given their machine for trial, and Y company also they have given their machine for trial. I'm taking same sample. I'm testing in a random fashion in both the machines. One machine is giving me a higher a normally distributed data with their mains rule stem. The another machine is also giving the normal distributed data. Um, yes, a normal distributed data. And if I compute their kurtosis, like by just looking at the curve, their population curves, it will be difficult for me to judge which machine is like giving the better results. So it is very obvious, like we cannot decide based on the strength because strength is a material dependent property. It can vary depending on many other factors. But when it comes to testing, now we have the data or statistics. Like based on that, it will be easy to decide. The statistics which we use for such kind of needs is the kurtosis. So kurtosis, like if it is high for the machine X of the company which has supplied the machine, X company which has supplied the machine, then it is very clear that their reliability is very low. It has widespread data compared to the another company which is having lower kurtosis value, which is like less than 3 is even more than. So now we are clear with what is skewness and what is kurtosis. So In this case, you can see this is a Cullen and Frey graph. Cullen and Frey graph have the square of skewness and kurtosis on the y-axis and square of skewness on the x-axis. And you can see here the uniform distribution has the zero skewness because they are not tending towards any sides. They are like symmetric without what's that? Not symmetric around the center. They are symmetric through. Means their skewness value is zero, and you can see the other distributions also which follows this logistic distribution. And then what else? Normal distribution, like it is having skewness zero because they are perfectly symmetric, but they have the kurtosis close to 3. These are all the a simple observation which you can make when as soon as you see a graph. So what I have did is like I have taken a data, instead I have generated a data normal which is normally distributed. One second. I have generated a data which is normally distributed using the code or norm. So now it will generate a normal data, 100 normal data with mean 0 and standard deviation 1. So then I am giving this command with descriptive distribution, which gives the summary of the statistics like what is the minimum value, maximum value, median, then estimated skewness and kurtosis. From this, I can from this also I can tell like the estimated skewness for this function is close to 0, which is like it's minus 0.04 is close to 0, and kurtosis is for close to 3. As I can see, this function whatever I have generated is a normal from a normal data. It also follows a normal distribution. So this way I can test my hypothesis whether they are falling under the normal distribution or not. Then similar way, I have generated a uniform distribution or uniform. Like similarly, 100 samples I have taken with minimum 0 and maximum 1. Then using descriptive distribution function from a fit distribution plus library. See, remember, you should install this fit distribution plus library before calling this descriptive distribution function because this function is in that library now. So if it is not there, we first download it using the install.packages and do it. Otherwise, we can directly call it in the library. Library fit distribution plus. I mean FIT, VASTR, PLUS, the command. So, yeah. They will be giving the summary of the statistics. In this case, you can see the estimated skewness is also close to 0 because of the uniform distribution, and the kurtosis is also less than 3. So, moving forward, what is the actual question? The question is asking us a given set of data can be characterized into particular distribution using Cullen and Frey graph. The x-axis and y-axis of the plot is respectively dash and dash. Just now we have seen the Cullen and Frey graph. The x-axis is square of skewness and y-axis is the kurtosis. So the correct option for this is C. Let's go to the fourth question. That what they have asked is in lecture 59, the probability of selecting a random point within a circle was used to calculate the value of phi using the simple Monte Carlo simulation. The choice of these random points were carried out by generating random deviates using R unit and RD unit functions. The error between the calculator and the original value of phi was minimum for. Okay. We can generate uh, a discrete uniform distribution as well as a continuous uniform distribution. And we can here generally what they do is like they calculate the error values. So when they calculate the error values, they are asking which function or which distribution will give us the minimum. So for this, the simple thing which we want to understand is like higher the information, lower the error is. So continuous random variables can provide more precise result uh, compared to the discrete uniform distribution because they have large range of values and have more precise probability distribution because they what is it in case of discrete distribution like let's say we have a distribution like this we don't have a proper PMF for this. But when we take a large number of data, as you know, like more than 30 minutes, they tend to, when they sample more than 30 minutes, they tend to follow the normal distribution. When they're following a normal distribution, we have a predefined function for that, which clearly fits this function and fit the given data. So we have more control over the data. We have several functions which can compute the various statistical parameters directly from that fitted curve. So we have higher control over the what is it, interpretation and calculations when it comes to continuous distribution than discrete uniform distribution. Hence, and you can see from here on the right side, I have taken a number of points and error percentage, probability of error, and with increase in using the Monte Carlo simulation, we have done this. I will share the code later. So in this, we can see with the increase in the number of points, the error is decreasing. So hence, in case of continuous distribution, I can take a number of points between two curves. But in case of discrete distribution, I don't have that I don't have that freedom to choose in between points because it can be completely different from whatever the previous points were. However, this has this complexity in the calculation because it involves large number of points, but we always know the accuracy and the time won't be like together. They will like follow the opposite ways. If you want higher accuracy, you have to go for continuous distribution, which takes more time for processing. However, they give the better results. Yeah. So far, I hope that everyone will be clear. Like, if you have any doubts, you can ask me. You can just, you don't have the facility to talk, you can just ask the question in the chat box. 2 minutes. Let's see, like, if someone is asking me, she can answer to it, otherwise, we can directly go to the expert. One question is like, in case of discrete distribution, each point, let's say like probability of rolling a die. If it is one means it has a defined probability, two means it has defined probability. How do we calculate the probability of a given value in case of continuous growth. So that is the question. So, like this is the question which one person has asked. So, how do we generally calculate it? Like, say, let's say, like if the distribution follows a normal distribution, then must we calculate the mean, then standard deviation based on the values or the population of samples is whatever we have taken. Then, then we transform it to from a normal distribution to standard normal by what is it, like computing the z score. Uh, then using the z score, we will check from the z tables. Like let's say, what is the probability of a student being uh, uh, less means what's the probability of a student being less than 160 centimeter height. So like that, if there is if some question is being asked me, you want to know the probability. It's like the probability is nothing in but the area under the curve in case of PDF. So we just calculate the area under the curve in PDF using the z-score. Yeah, first we find the z-score, we use it to express you by so using that we find the z-score, then using the z-score we compare with the z tables and we can compute the probability one, right? Like 0.6 or point 0.5, something like that. So this is how we generate. Any other question? Let's go to the next question. Before going to the next question, let's discuss about the bootstrap method. So what is bootstrap method? So if you have a population, it is having n number of data sets, uh, and we want to understand their behavior. So what we generally do? Let's make it like more clear with uh, well-known example. Um, okay, again, let's say like if you want to know the population which is using the mobile phone for between 4 to 7 hours. So that we want to know. So for that, we cannot, in our population, we cannot, first we need the data. For that, we cannot just go and calculate the average usage time for each and every individual because it will be like time consuming because like we have around many million population. In that it will be very tedious to go and ask each and everyone. Hence, what we can do is like we can give a survey or like we can do a personal interview with some fixed population or like we can take some 100 population or 200 population or even 10 or 10,000. So like that we can run like n number of surveys. From that survey, we can try to like for example, if survey one gives this much, like if I okay, in the survey I have got uh, this kind of result for each and every survey. Now I will take the mean values and plot it like a histogram. So when I plot it like a histogram, the higher average value which is reported will have the higher intensity. So in this way, I can minimize the time by not going and computing in each to with each and every individual. And with with increase in m number of values, the accuracy will also increase. It won't like tend to the error won't be that much compared to doing with very limited size. Yes. So I think how you got it right. Like bootstrapping is nothing but it's like it's resampling. We'll take one sample. We find the average or like it's not only average or it can be standard deviation. It can be some quantile. So it depends. It changes from the it changes with respect to the need. We want to understand their standard deviation means I will go with standard deviation. If I want to understand their distribution of mean means I will go with the mean. So likewise, I will calculate for one sample, then again I will look for next next sample, I will be keep on resampling like for n number of times. So what is the beauty of this? It's like once you have a fixed set of the data, from that with this resampling, you need not calculate the specific required value again. Rather, you can with the available data, you can get a better estimates. So that is the advantage of bootstrapping. It saves time and money. So here the question, like the question is regarding this bootstrap. So what they have asked is consider the following data from they have given a DOI for a journal. In that, which of the following is diagram obtained using the bootstrap method correctly represents the data. So on this one, two, three, and four histogram curve, and they are asking the given data, which represents the closely represents the generated data. So for that, before in hand, we should know how to do a bootstrap operation in the R language. So for that, first we need to define the library boot because the because the boot function is available only, sorry, the bootstrap function is available only in this boot library. So first we call this library into a program using boot. Then here I have given the values in terms of array or one dimensional array. Like lat is my variable. Lat is given lat. The value is given by C of 547.10. Likewise, I have given all the values. And next, we have to define a function to calculate the mean. So we know like what we want to estimate from this group of data. For that, we have to define a function which clearly tells the code that this is the one which I am looking for. Here, mean is the one which we are now looking for because here they have told right. So the following step of optimization bootstrap method. Okay, so this is like mean only. So here we are just defining a function name called mean f1, which means mean function is the mean function is function of data and its indices. So data means the data means like it is like n number of data in a given population. In that we are choosing only the few indices. So these are the indices, and so mean. So this is like we generally define that f of x, like that we are defining function of data and indices, and what is the function which we are defining for this is mean of the data. Mean of the data. Data is like a whole of the given indices. Indices means whatever data we have given. So basically, mean of the that is what we wanted to find. So now the statistic function is defined clearly. That is, we want to find the mean. Then using the boot, we want to compute. So we are storing the values in boot results. It also will store it as array. So boot of data. Data. First, we have to define the variable for which we are planning to do the or the sample which we are planning to do the bootstrap. Then statistic equal to mean function. Already we have defined the statistic function. Then R is equal to 1000. R is like 100 times below the result within the given limits. Now we are plotting the histogram of the bootstrap replicates, whatever we have generated. So this is the function which we generally use, is to boot results. Then uh, in my case, like I have represented the column values in T, so it is directly taken from that. So breaks means second. Breaks defines the bin. So about that. So breaks means how many bins you are looking for. Like bins means it can be 30 bars or 20 bars. Here they are taking the we have taken breaks as 30 breaks or bins, 30 bins. Then main will give the title of that, bootstrap replicates of main. Then X library, X labeling is mean column, color is gray, then border black. So using that we have generated the histogram plot using the bootstrap method replicates. Like the beauty is like we only add uh, nine data. How we have generated the bootstrap using bootstrap, we have generated 30 data. So if you see here, so mean value falls something close to the 546.9 something, like close to 547. So the one with the curve which closely resembles this, like we'll see from the V. So it is like right side skewed, but it is exceeding more than the mean value is exceeding more than 547.0. Hence, this is not the one. Okay. So if you compare this with this result means it is kind of symmetric, but the curve is not symmetric with 546.90 as the average. This also that indicate our curve. While if you see the it is like far away from the our average value. Our average value is close to 547, 546.97 something. So this is also not the curve. So the curve which closely resembles this is because we have 546.97 those 546.97 we have the mean value, and then we have the tails so very closely resembling the our function bootstrap abilities. So answer for this is B. Let's before going to the next question, let's discuss something about the exponential function. So, as we have seen before, exponential function is kind of it's a continuous distribution function which has the extreme values on the right side, not on the left side. Hence, the curve will be like curve will be- then this is p or an x, whatever the variables. So, whenever we see a problem which closely resembles for exponential distribution, which will also be closely resembling the Poisson distribution. Then we will also always have confusion. Which function should I go with? So basically, Poisson distribution or the Poisson occurrence means the event occurring with a given time interval. So Poisson distribution means the number of events occurring in given unit. Whereas if you see the exponential distribution, it is like time taken for the first event or like time taken for an event to occur. So it's like opposite of a Poisson. If you consider like if I tell like it took 10 minutes for me 10 minute intervals between an event to occur means the number of event occurs for given time and so by 10. So this is like exactly opposite of Poisson distribution. So another yeah, strikingly difference which you can easily observe is they are continuous in nature. Exponential function distributions are continuous in nature, but whereas Poisson distribution is discrete. So the PDF of probability density function of exponential function is given by this f of t is equal to lambda. Lambda is the parameter of this Poisson's parameter or rate at which the event occurs. Lambda into exponential of minus e power minus lambda t. So yeah, let's see the example so that it will be easy for you to understand. So let's take a classical problem in metallurgy, that is crystal growth problem, where you suppose you are studying the growth of a metal crystal in a material, and you have computed this. The time it takes for a new crystal to form is following an exponential distribution. Can follow an exponential distribution. Then we can predict how long it will take or it might take for the next crystal to appear. For example, if you're studying a solidification problem, and just a minute. You are looking at, you are understanding, you are trying to understand a solidification problem. In the problem, this crystal nucleation depends on various factors like temperature, impurity, composition of the alloy. And if you want to model the time it's taken for the new crystal to form, because nucleation even depends, decides the various things. The nucleation rate is high, but crystal growth rate is low, means then actually it can tend to form a finer grain size compared to the uh, sluggish nucleation kinetics. So this can significantly influence the material property. Hence, understanding the nucleation kinetics is very important. This nucleation kinetics can be well explained with the exponential distribution because the time taken for the nucleation event is it can be computed and it can be modeled with exponential distribution. So they are observed like I've taken an example here. We observe that on an average, a new crystal forms in a metal every 10 hours. Rather than 10 hours, we can take it like every 10 microseconds. Every 10 microseconds. So we assume that time between the crystal formation follows an exponential distribution. So average rate of occurrence can be given by 1 by time taken, which is 1 by 10 is equal to 0.1. So probably that a crystal forms within the next 5 probably that a crystal or a nuclei form in the next microsecond is given by P of t less than 5 to be equal to 1 minus exponential of minus lambda t. 1 minus exponential of minus 0.1 into t. T is like 5 microseconds, so into 5. So we get there's a possibility that 39.3 percentage possibility that a nuclei will form in next to 5 microseconds. In 5 microseconds. Okay. So here you might get a doubt. You might get a doubt. What doubt you might get is like this is how the exponential distribution is. Exponential distribution is will look like with probability higher on near the origin and with decreasing probability with increasing time. So let's say like here we were discussing like crystal will form in every 10 seconds. But we were computing for the fifth second. Or like even if they compute for the 1 second, then area under this the area under this will be still high, right? Like compared to if we compute for more than some seconds means the probability of getting probability for the nucleation event is high when it is close to zero. So you might ask this question: how we can understand this? Because the probability is we are told like 10 seconds is it is taken on an average for each nucleation, but how the probability is high for close to zero. So the explanation for this is we are only looking at let's say like what if it doesn't nucleate at 10? What is the probability that it will nucleate at 10.1 or 10 point? So it is still high, right? Like uh, compared to like 20 seconds, 10.1 or 10.2 instead of exactly happening at 10, probability of happening at 10.1 or 10.2 or 9.9 is still higher because it is close to the average. Similarly, to go back 10 seconds, like the previous event also would have occurred close to this, like 0.1 or 0. So that probability also higher. So both are same. If you are just seeing the particular event, if before also close to zero also an event can occur. So that is what the meaning is. I hope it is clear. If you don't understand, I can explain it again. So okay, let me tell this again. Try to put in this way. So we are just looking like average to be 10 seconds. But before this, like before this 10 second, there's equally likely that in the near the 0 second, an event could have occurred because every 10 second it is occurring, which means like the 10 second before this is 0 seconds, and it may not exactly occur on 0 second. Rather, it could have occurred on 0.1 second, right? It still has the higher probability, which is because it is close to the average value. So that is what I am trying to say. So even though it's close to zero, uh, it has the it has the highest probability because generally even if you take the normal distribution, the higher probability will be close to the mean. Yeah, the mean is 10, but still the curve is not like this. Rather, curve is not like this. Rather, the curve is like exponential. That is because of this. The rate of occurrence doesn't change. It's a constant parameter. Hence, before 10 second also, uh, it is like if I have started from here, let's say origin from here. This is my 10th second. So uh, it has still has a higher probability than the 20th second. So that is what it is trying to uh, tell us. So if you want to model this in the or if you want to put this in our language means first we have to define the lambda. Lambda is given by or lambda is equal to 1 by 10. Then probability function we have to define. So like we have defined for the median function, we here define the probability function. The x underscore time is given by function of time t with the function we are defining as lambda into exponential of minus lambda into 2. So now we are trying to compute the probability that a crystal forms within the next 5 hours. So it is like within, okay, this I think I can explain it. Within next 5 hours means we are computing area under from 0 to 5. Within 10 hours means we are computing 0 to 10. What if they ask more than using this formula? But what if they ask more than 20 or 10 hours means just simple, drop this 1 minus and just represent, just write it like exponential of minus lambda into t. That is enough. It is more than given time. Then this just exponential to t. This is what we are become. Okay, here it is very clear. Like within 5 hours only they are asking. So we can use it as we do it traditionally, like 1 minus exponential of minus lambda into t. So using this, we can just have to print the value. Uh, we'll get the answer for this. The next question, sixth question. The sixth question they are asking. The well-known method of radiocarbon dating is using the process of radioactive decay of C14 atom to N14 atom. In such process, if C14 atom decays to N14 atom in 10 years, it occurs in 10 years, so 10,000 years. Yeah. So the rate of occurrence is 1 by 10%. So it's very clear. Lambda is equal to 1 by 10%. What is the probability that C14 atom will decay in N14 within 5,000 years? Actually, it will won't take 10,000 years. The half-life period is uh, 573 by this. 573. Okay, just no, for the sake of this problem, give me a minute. For the sake of this problem, we are taking it as 10,000 years. So rate of occurrence lambda is equal to 1 by 10,000, which is what calculated here. And we have to determine the probability that by decay is less. Decay will happen within 5,000 years. Probability. P of t less than 5,000 is given by 1 minus exponential of minus lambda t. Here lambda is 1 by 10,000, which can be written as 0.0001 into t is 5,000. So then we calculate this can come up to 0.393. It is 39.3% chances that if the C14 will decay within 5,000 so 5,000 years, provided the rate of decay is 1 by 10%. If you want to code this in the R, what is how we will do it? That's the next question. So before that, we should know which function we are going to use. So we use the function called p of exponential. P will give the probability distribution function. Um, for this cos. D is the density function. It gives the exact probability. But P is the cumulative distribution function. Here we have to compute from 0 to 5000 hours, right? So we are using P. P is the cumulative distribution function. P exponential of Q, comma rate, comma lower tail, comma log T, dot P is equal to cos. So this is the general syntax for this cumulative distribution function using exponent for the exponential distribution. So CDF for the exponential distribution. So here if you see what is going to be Q is the value at which to evaluate the CDF. For example, here the 5000 is the value to which we have to evaluate the CDF. And rate is the, as I told, lambda. Here lambda is 1 by 10,000. Then lower tail is equal to lower tail, the log value indicating that to calculate lower tail probability per tail power. Tail probability okay. Now I am very clear about this. See, when we are computing this exponential function, we have done this like if you want to find here we don't specify anywhere till this rate that we want to find from left to right or right to left. For example, whether it is within 5000 years or more than 5000 years. So for that, this lower tail will fix that limitation or control. Whether we should look for the lower tail. If by default it looks the lower, that means lower than given specified values from the tail. If it is upper tail means it will compute from here to the infinity. This side. You also can calculate lower tail and we want to get this side. Calculate lower tail and subtract it with 1. That can also be done. So here lower by default it is in the lower tail proof, which makes like it computes from the 0 to the given value. This area. False means it will go for the given value to the infinity. Okay. So log dot t, okay, this log dot p will or log just log will indicate that whether to return the value in the natural logarithm or of the CDF or just CDF value itself. So it generally we leave it like false, so that we will get it in the um, normal value. So here we want to know like here the output snippet for this is as we know the Q value is 5,000 till which we have to find the CDF. The rate of occurrence is 1 by 10,000. Then it should not return in the log value. Just we need it in the CDF value as a CDF value. So hence the snippet which closely represents our need in the sixth question is the seed. So yeah, next is select the correct course method that will calculate the area under the curve of the chi-square curve with degree of freedom 7 for the interval from 6 to infinity. Okay. So first we want to understand the chi-square distribution syntax. The syntax is chi-square. P-C-H-I-S-Q. It's for the CDF function. Q is the quantile value at which we have to evaluate the CDF. Then DF is the degrees of freedom. Then lower tail means a logical value indicating whether to calculate the probability from lower tail or from the upper tail. Okay, here we don't have to specify the interval because okay, here we have to specify the interval from 0 to 6 or from 6 to infinity. Or instead, what we are trying to do here is like, as you know, the chi-square distribution will look like this. It is like skewed towards the right. I can show that chi-square distribution. Whether I have it or not. Yeah. Generally, they are represented like this. With peak, their being asymmetric, like first is genus with higher amount of extreme values or pertussive values. So now we want to find from 6 to the infinity. So we have to enable the lower tail false. Like so these chi-square distribution of quantile up to 6. From 6 we have to find. So all the 4 having the same option. Degree of freedom is 7. All the 4 option is given just given the same degree of freedom. Lower tail is equal to false. So this by default it is true. We are also true. So wrong. We want to find from the upper tail. Hence it is false. So this is the correct checkpoint. The eighth question is done. Let's move on to the ninth question. Suppose you want to plot the probability density function for a normal distribution in R with mean 0 and standard deviation 10 on a log scale. Where the x-axis range is 0 to 1, which one of the correct, which one is the correct coordinate function? So they are given like mean is 0, standard deviation is 10. It's where x-axis ranges from 0 to 1. So for this, and they want to plot the curve also. So curve with the option to plot. Then D is the density function. So L norm is log normal, PL norm of given variable x. Mean, okay, first we will see the syntax. Syntax is DL norm of x, comma, mean log is equal to 0, comma, SD log, comma, log is equal to false. Like, which means whether it should return its value in log or not. So that is what the meaning. Mean of x is the numeric vector specifying the value. At least we have to evaluate the PDF. The mean log is the mean of the underlying normal distribution. Like and SD log means standard deviation of the log normal distribution. Then log it should return the values in terms of logarithm or PDF values in the terms of logarithm or like as it is. So here the one which is most close to this is here. This one didn't mention from which value to which value, or it didn't specify the mean or standard deviation, so this is not correct network. So which means A is not the correct one. Then D has specified the value, and then mean log and SD log, but they have not specified the command. So now it is between either of these two. So in this, our next range we have specified from 0 to 1. So And also standard deviation is 10, not 1. So this is not correct answer. C is the correct answer. So this is the syntax for the curve. Curve, it's expression, which is like it can be a like we have specified here, right? DL norm or can be arithmetic operation, whatever. Then from which value to which value we can specify from lower limit of the x-axis range to upper limit of the x-axis range, and n is the number of points to evaluate. Then add um, then we should add the logical value to the existing plot. Like the plot will have the values or type of curve. It's like a point plot or line plot, or whatever as per the requirement. Then X name and Y name for the labeling of X and Y. Which of the following figures is the plot for the probability density function of log norm mean zero standard deviation 0. So previously we have discussed about this. Here just explain the command of syntax for this is curve of real norm, x mean log, sd log, then from which value to which value. So this is what we have to specify. So here we have specified x values is ranging from 0.01 to 1 with the interval of 0.01. Then it has generated 100 values. Then using the command curve, we have generated the plot uh, using DL norm. X is from sequence. Then mean log we have specified 0 as given, and then SD log is 0.5. From minus 20 to plus 20 because the whatever representative figure they have specified goes from minus 20 to plus 20. So this one resembles close to the requirement, the given figures, so we can consider this. So with this, we are done with today's problem. If you have any doubt, you can ask me.